Apple II forever, making life better and better. Apple II forever and ever, bringing the rainbow to you.
Hello, my name is Oliver Schmidt, and I'll talk to you today about purpose-built software-defined hardware with the A2Pico. I guess many of you have seen my last year's presentation about A2 RetroNet. So let me start with an overview of the project evolution. Last year, the name A2 RetroNet was used both for the single firmware and the prototype hardware. By now, the A2 RetroNet is the name of one specific firmware project. There are several firmware projects, and they all use together a library which is called A2Pico. And additionally, the hardware also has been named A2Pico. Let's have a closer look at the hardware evolution. Last year, I presented a prototype that was developed together with Glenn Jones. This prototype used a bus switch for voltage level shifting. This was the fastest possible solution, and it was only available in SMD. This year, I'm not using a prototype anymore, but a ready-to-ship product. It's developed together with Ralle Paleviv, and it's using transceivers for voltage level shifting. These transceivers are slower, but as I know by now, they're still fast enough. The benefit is that the design is available both as SMD and through hole, which is very do-it-yourself friendly because there are no chips to be programmed at all. Okay, so after having this clarified, I'd like to take a look at modern Apple II expansion in a more general way. I see a trend towards all-in-one designs. For example, if you think about a fast CPU of course requires fast RAM. If you have fast RAM, you might think about having your mass storage I/O coming from some SD card work directly with that fast RAM instead going over the rather slow Apple II bus. And if you're at it, maybe you want to have your video out going from that fast RAM instead of the slow bus. This allows you nice video modes to be accessible via DVI, also known as HDMI. What you end up is something that more or less is an own computer and pretty much only uses the PSU and the keyboard from your old Apple II. Another thing is, think of cards that sit in one physical slot and have a certain functionality. Then you have a virtual card with another functionality sitting in another slot, and yet another virtual card in another slot, and so on and so on. So you end up with one physical card that looks to the machine like a lot of virtual cards, meaning the other slots of your machine cannot be used anymore. So please don't get me wrong, those all-in-one designs are, of course, from a technical perspective, really great things and really cool features. But is the outcome then really still an Apple II? Or are we rather having a wag the dog situation here? It's, of course, your personal opinion, how you think about this. My very personal take is that I would rather not want to replace any mainboard functionality, but rather augment the mainboard functionality. And I personally believe that one physical card should only use one logic slot and not have virtual other functionalities. And in general, I believe it's a good idea to stick to what the Apple II reference manual says about Apple II peripheral cards. In this context, a peripheral card is basically about three things. It's about the I/O space. There you have 16 addresses, which are usually connected to certain I/O ports that trigger certain hardware functionalities of the card. Then you have the card ROM space. Here you have 256 bytes of address space that can exclusively be used by the peripheral card. Usually there's a ROM here. Usually people call this also the slot ROM. And finally, there's the expansion ROM. This is a 2 kilobyte address space that is shared between the peripheral cards. I will come back to this later in my talk. So, although the A2Pico is a software-defined hardware solution, it deliberately stays within the limits of such a classic peripheral card specification. That implies, for example, that you will never be able to build a graphics card based on the A2Pico design, because that would require you to access the video RAM, which is outside the specification I just showed. So the question might be, can you build something interesting within this limited scope? I believe yes. For me, in general, the Apple II is all about being creative within certain given limits, and this is also true for the A2Pico. So looking at it sort of from the other side. Although the A2Pico is a classic peripheral card, from the developer perspective, it still offers all the advantages of software-defined hardware. Additionally, all 7 currently published A2Pico firmwares are based on the same shared A2Pico software library. That library shields the developer from the low-level details of building an Apple II peripheral card. Rather, he can focus on implementing the 6502 code for the emulated ROM and build the C code that defines the actual behavior of the card. From my perspective, A2Pico basically brings 2 innovations to the table. It's a really very affordable price for the end user, and it's surprisingly low effort for firmware development. The latter means that you can approach a project in a new way. You can really do a top-down approach, meaning you first have your overall software idea, what your project is supposed to do, and then you think, it would be great to have a certain hardware in place for this purpose. And then you just build the hardware for exactly this purpose. After a quick recap of A2 RetroNet, I will show 2 examples I will call interrupt, inversion, and page streaming. So let me take a quick look back at A2 RetroNet and show you what I mean with being creative in given limits. A2 RetroNet is about providing mass storage I/O and character I/O in a single slot. In general, there's no technical problem about doing that, but the problem is making the Apple II understand that in a single slot you have both functionalities. Usually the Apple II understands about a functionality in a certain slot with the so-called ROM ID bytes. And the ROM ID bytes for mass storage I/O and character I/O contradict each other, so you cannot have both. However, Protos only cares about mass storage I/O, but not about character I/O. That means any program that does character I/O, for example, doing a printer or call a modem, will have to manage this on its own and think about the slots and finding the device on its own. This allows us to do what you can think of a Janus ROM. During the boot of Protos, it looks like a mass storage I/O card, so Protos will understand and use it as mass storage I/O. Afterwards, after booting, you can switch the ROM to look like a character I/O. This doesn't hurt Protos anymore because its detection process is over, but now other programs can detect this character I/O card. So this is what I mean with trying to find new creative ways inside the given limits. Interrupt inversion. As the name implies, this means that we are going to do something in a, let's say, opposite way than it would be done usually. So let's first start at looking at the more traditional ways of doing interrupts. Normally, interrupt-driven I/O is desirable for 2 reasons. First, We want to get the incoming data as fast as possible from the device into a main memory buffer. For example, a serial interface chip has just a single byte of device buffer. Additionally, the main memory buffer is also size limited, so it may also overflow. In certain scenarios, in the area of network I/O, we therefore want to signal flow control to our peer in order to make him stop sending further data as soon as possible. However, it's important to understand that interrupt-driven I/O usually does not result in fast I/O. First, the interrupt itself brings quite some overhead into the machine. The ROM processing and the operating system processing, there are a lot of CPU cycles going into this for each and every interrupt handler. And the second thing is, just having the data very quickly into main memory doesn't help. The data needs to be actually used and processed. And this is normally not done inside the interrupt handler. It's done by the foreground program. So having the data quickly into main memory does not speed up anything in any way. Modern network I/O devices usually have pretty large device buffers, maybe much larger than the amount of main memory one would want to reserve for this purpose. Additionally, they usually handle flow control automatically based on the fill level of their device buffer. What does that mean? First, interrupt-driven I/O is basically unnecessary because the device buffer is large and it never overflows because of the implicit flow control. And the foreground program can process the data right out of the device buffer very efficiently. But it's not all. Interrupt-driven I/O is actually harmful because reading the data from the device buffer eagerly hampers the automatic flow control of the device. Means the peer thinks that we are just fine reading more and more data, which is not true because we're just getting the data interrupt-driven out of the device. But where do we process it? And additionally, just the interrupt handling, as mentioned before, wastes a lot of CPU cycles we can spend otherwise by just not using interrupts. So now that we got interrupts out of the way, let's have a look how the foreground program actually accesses the device buffer. Usually this is a FIFO. That means the foreground program just repeatedly accesses a certain I/O port and gets one byte after the other from the I/O port. That's very nice and efficient. But when it's about a network, you always have the problem that there might be no data available at all right now. Usually, you need to check if there is data available by looking at some status bit, and only if the status bit says that there is data available, then you can read it. We can see this in the second code. But if you look at it, this means that instead of the 4 CPU cycles for just loading the data, we are already there now by 10 CPU cycles. And this is just for the hopefully unusual special case of no data being available when we expect it. So, wouldn't it be great if we could let the program just read the data, read data, and only in the case there is no data, do something special, keeping the program from trying to read data in the first place? The question is, could we maybe generate an interrupt if a FIFO is about to become empty and therefore keeping the program from reading data? Generating an interrupt is a usual way to describe it, but not a very good way to describe it. Let's look at this. Interrupts aren't a pulse, they are rather a state. So the device sets this state. You call it asserts an interrupt. Then there is some CPU handler that does stuff with the data that's coming in. And additionally, always it does something with the device that makes the device deassert the interrupt. And then the interrupt handler returns. And if the interrupt handler would not do this deassertion of the interrupt, it would be called again and again and again right away, and therefore the foreground program would not have any chance to run. So it would it hangs. So with this background knowledge in place, we can now think about using our software-defined hardware approach to create a hardware that asserts an interrupt as long as its FIFO is close to being empty. The interesting thing is that this device does not require an interrupt handler to deassert the interrupt. It can deassert the interrupt on its own as soon as the FIFO fills up again by data flowing in from the network. So therefore, we can have two ways of interrupt handlers. We can have a trivial interrupt handler that basically does nothing. It just returns right away. This interrupt handler is executed again and again and again until the FIFO fills up and therefore the interrupt is deasserted. Then the interrupt handler is not executed anymore and the program continues to run where it was and starts to read from the FIFO again. Exactly what we wanted to do. On the other hand, we can have a more typical interrupt handler. This interrupt handler actively checks the FIFO in a loop inside the handler until it's not close to empty anymore. This interrupt handler is only executed once in such a scenario. The idea is that inside the loop it can also, for example, check the keyboard for some escape key, allowing the user to quit from waiting. And on entering the interrupt handler, it could provide some visual feedback. Think of just having the high-res screen turn on those bottom 4 lines of text, and on these 4 lines something is written like waiting. And as soon as data comes back, the interrupt handler quits the loop and the 4 lines of text are removed again and the program continues with its usual operation. So with interrupt inversion, we are not wasting any CPU cycles at all in the usual case of data nicely flowing in. Only if there's something specific, unexpected happening and the data is not there, then we do something special. And in general, let's summarize. Traditionally, an interrupt means that something needs to be done urgently, and the foreground program not running is just an unwanted side effect. With interrupt inversion, the interrupt is asserted when there's nothing to do, and the fact that the foreground program doesn't execute is exactly what we want to happen. And this is why I call it interrupt inversion. And by the way, something like A2Stream would be pretty much trivial to write based on such a software-defined hardware that implements interrupt inversion. Page streaming. Yet another rather specific approach to, let's say, a more special scenario. With a traditional way to implement hardware, you would rather not invest the effort. But with software-defined hardware, the way you do it with A2Pico, it's so simple, it's so easy that it's a viable idea to implement this. Let's see. Let's assume the scenario at hand is video playback. Of course, we don't have any cycles to waste for whatever decompression of the data. Video playback on a machine like the Apple II is about getting the bytes from some source and pushing them as quickly as possible onto the video screen. That's all. Of course, we only want to set the pixels on the video screen that have changed over the last frame. So our memory access pattern will be random access, sparse, not one byte after the other, because we don't know beforehand in which areas the video screen has changed over the last frame. So the data we are reading likely consists of pairs of a byte we want to write into the video screen somewhere, into the video RAM, and then the address where to write it. If we think about typical 65C O2 code to do that from a FIFO device, it would look like this. We would load the value from the device, then we would load the low byte of the address, the high byte of the address, then we would store the low byte and the high byte of the address into the 0 page in order to allow us to do an indirect store. Then we would store the value at the address. If we calculate this, this means that we have 23 CPU cycles for processing a single byte. This is not nice. The 6502 can work much faster with data that is, let's say, embedded into the program. So we might have the idea of seeing this data not something we access, but seeing this data as something that we execute. So we would prepend each of the data bytes with a load accumulator instruction, and we would prepend each address with a store accumulator at an absolute address instruction. So the 3 bytes making up the value and the address would become 5 bytes, starting with load accumulator immediate, then the value, then store absolute, and then the address. Looking at this in the typical way of writing 6502 code, we have an LDA, immediate, SDA, address. This means only 6 CPU cycles, which is nearly 4 times faster than the 23 CPU cycles we had before. Of course, the CPU cannot execute bytes from a FIFO. We need to have those bytes we want to execute in some memory location. And we are trying to do this from a peripheral card. So what are our options? Fortunately, as we've seen before, a classic Apple II peripheral card can contain a 2 kilobyte expansion ROM. It's not uncommon for more complex peripheral cards that those 2 kilobytes are just not enough to contain all the instructions necessary for operating the peripheral card. There you then have 4 kilobytes or maybe even 8 kilobytes of expansion ROM. But the address space that can be used by the expansion ROM is, of course, always the same. It's limited to those 2 kilobytes. And therefore, larger expansion ROMs need to use paging. They have several pages of ROM, and there's some way to switch back and forth between those several pages of ROM. Usually, there's a page register that allows the CPU to select the page it wants to use. Coming from here, it's surprisingly simple to go to page streaming. Instead of just having 1 or 2 or maybe 4 pages of expansion ROM, you are going to have a lot of pages. And the CPU doesn't select any of those pages explicitly, let's say page 2 or 0. Rather, it says, I'm going to move on to the next page. The pages that it used before are not accessible anymore, but they are not necessary anymore. That's all. Look at the implementation. The Raspberry Pico has 2 megabytes of flash memory. This won't get you far when it comes to page streaming. But the A2Pico card has a microSD card slot. The Raspberry Pi Pico has 2 ARM cores, called Core 0 and Core 1. Core 0 reads the expansion ROM pages from the microSD card. It uses this with a DMA controller. The Pico ARM Core 1 answers the expansion ROM read requests from the CPU. There, the innovative PO architecture from the Raspberry Pi Pico comes into play. So imagine it like this. Both ARM cores share two things. First, they share an expansion ROM page ring buffer. It has 8 entries. This is a data structure that core 0 writes to and core 1 reads from. And then there is an expansion ROM page read request queue. Well, again with 8 entries. Here, core 1 writes to and core 0 reads from. And this way, both cores put these data back and forth, and the CPU sees just those pages flowing in. Okay, let's summarize. Page stream means we have basically an infinite number of expansion ROM pages. This allows us to do infinite loop unrolling. Every load instruction can just load an immediate value, and every store instruction can have a fixed address. This speeds up code significantly. At the end, it allows us to answer the question, what can the Apple II do if we equip it with an infinite amount of RAM? Some further thoughts. The 6502 code in the expansion ROM pages might be generated just in time, based on some network data, for example. This might then be nicely combined with interrupt inversion. Okay, so what I really want to show in this talk is how easy it is to create new software-defined hardware with the A2Pico. Therefore, I've created a really silly hardware that is only capable of just playing a single demo. Because I also want to showcase the capabilities of the Apple II GS, it's using the 2GS film mode for video, and it's using the GS and Sonic audio chip for creating a nice stereo 26 kHz audio. For the audio, I'm using what I call a raise the oscillator accumulator approach. That means the oscillators run in free run mode, not generating any interrupts or alike. I'm just making sure that I replace the content of the DOC audio RAM in the right way, so that by the time the oscillator accesses a certain memory location, the right content is placed there. The demo, by the way, runs at 1 MHz because all memory that is touched is on the slow side of the machine, which is the video RAM, the Ensoniq I/O control ports, and the peripheral card expansion ROM. Everything is on the slow side, so this is pure 1 MHz. I only needed less than 30 lines of new C code for the page streaming. This shows really how simple this can be. For the actual data, I used FFmpeg to process the original video, did some filtering, downscaling, created a big bunch of PNG files. I used Audacity for resampling the audio track. And then there is a custom written C program that does basically two things. It does a delta generation for the film mode, and it does the audio-video multiplexing. And the output of this C program is the 65CO2 code that goes into the expansion pages. In this case, we have 80 megabytes of 6502 code sitting there. And this is played in roughly 3.5 minutes. On the GitHub page of this firmware, there's also a YouTube link where you can see the demo in case you cannot, for example, listen to it very well. I don't know what audio quality you here have. It might really be nice to listen to this with, let's say, high-end hi-fi equipment, or at least a headphone. Yeah, enjoy. So, I hope you enjoyed the demo. Let me emphasize again that A2Pico is open source, both hardware and software. And quite some effort went into creating the do-it-yourself friendly through-hole A2Pico, so just go ahead and build your own. And for everybody else, fully assembled SMD A2Picos are available. First, for worldwide delivery from Bulgaria. And recently we have a reseller in the United States. So I guess you can there get it faster and more easily. It's supposed to become available very soon there. So maybe you want to subscribe and show your interest. Thanks for your attention. And this now opens the Q&A.
One question I had, there was a couple different links. You said one of the links is to the project with like a through-hole version that would be suitable for somebody who, only knows how to do through-hole soldering. Is that correct?
Yeah. Yes. On Radis website, on the GitHub side, you can have Gerber files for a through-hole variant. You can just get the board produced by the usual suspects and then populate it on your own. And again, the interesting thing here is it's just a bunch of standard chips and no CPLD or whatever to program, which is usually already then getting somewhat complex. And actually getting this all done without any CPLD was the primary effort I put in here.
Excellent. Eric Rangel is asking how much can be crammed onto a floppy disk using this technique.
I don't know. The point is that this is, I think there was some years ago, there was a demo where it was about streaming data from a disk to drive, right?
Yes.
Without not having any sectors and whatever, just using it as a stream of data. I think this is pretty much the best you can do there. I would think was really great demonstration. Yeah. I would like to, I'm looking at my slides. I think I would like to add one aspect. Maybe for one or the other, it looks like, let's say 2 years ago, Oliver presented something about cool audio on the Apple IIe, and now it's cool audio and video on the Apple IIgs, so it's sort of similar. To me, this is totally different. What I presented 2 years ago, that A2 stream was, let's say, a tour de force, a multi-year project. And it was really bringing me to the edges of what I can do. And to be honest, it was sort of, let's say, showing off what I can do as an Apple II software developer. This is totally different. It's really on the opposite side. This is just, let's say, 2 or 3 handfuls of C code that go into this hardware. It's supposed to show that it's really super simple. And apart from the need to acquire some knowledge about the Ensoniq chip, this was of effort from, let's say, maybe 2 weeks or 3 weeks, this demo. So it's really totally different. And this is the point I want to make, because of course, with other hardware approaches, you can achieve much more and you can achieve much more, let's say, interesting things, but they are very complex. And this here is really totally simple, that simple. That's the point really I would like to make.
So I'm actually curious. We heard from Ed and Joshua earlier, and they ran into a lot of difficulties with the Apple II GS, partly because they weren't familiar with it, and also just because it is so very different. And I'm just curious about what is your past history with the 2GS? Like, did you find it equally difficult, or do you have more of a background in that?
It's surprisingly, let's say, I would say it's the other side of the coin of A2Pico being so, let's say, primitive from the Apple II perspective. What I said before, this just being a very basic peripheral card in the very sense of being a peripheral card. This means that it stays totally in the boundaries where the Apple IIgs creators thought about full compatibility. So this project, apart from actually requiring the super high-res screen and the Ensoniq chip, it has nothing special for the Apple IIgs. So there's no specific code, there's no workaround, there's no whatever in the A2Pico. A2Pico stays to the very simple basics of Apple II bus access. And therefore, it works, just always worked out of the box on the 2GS.
Oh, that's fantastic. Yeah, I mean, I guess just keeping it so simple actually was a huge advantage in this case, right? Like maybe the more complex your hardware, then the more, platform specific problems you might run into, I guess.
Exactly, perfectly. You really phrase it perfectly, because the point is, I stick to these ideas with these, let's say, only a 12-bit bus access and using these signals, IO cell, dev cell, and dev IO strobe. And these are the signals where the Apple IIgs is perfectly compatible, or nearly perfectly compatible to the other machines. As soon as you start doing your own address decoding, then you won't get into trouble with this M2 cell line, where it's about that the Apple IIgs brings the upper 8 bits of the address bus at a certain point in time on the address bus. And there you run totally quickly into all kinds of compatibility problems. And A2Pico deliberately stays clear of all these types of things.
Great, great. Let's see, there was just a couple questions. Someone asked if the slides for the talk will be made available.
Yeah, for sure.
Okay.
I would love to send them, or I would actually prefer if they would be made available somewhere on the KansasFest site in some archive area. That would be my preference, because I've created them exclusively for this event, and I think they sort of belong here, therefore.
Okay, that sounds great. And I think the code for the actual demo that's on your GitHub already, right? That bad
Right.
Apple IIgs, is that okay?
It's the GitHub is public since a few minutes, and the video is published since a few minutes. I actually postponed all this to make sure that you are the very first ones to see this demonstration. I really held it back until this very session, so it's sort of a exclusive prime.
Great, thank you.